Okay, so we're now going to move on to the next topic in mechanics, and we're going to start looking at velocities and more mainly constant acceleration. So let's maybe just have a think about what acceleration is. So if we start by thinking actually what we're getting from acceleration, maybe we're going to start from a distance. So if we're moving something, a velocity and a distance, is we've been shown at school that speed equals distance over time. Okay, but when we can think of this from a calculation, well, a calculus point of view, we'll call that v. So perhaps we could say that our velocity is equal to the change in d over the change in t. Okay, so this is just using a little bit of calculus. All right, so what happens now if we were to say what's acceleration? Well, what we've previously said is that our velocity, if we think it down to calculus again, how we're changing on a path, well, acceleration means that we're constantly changing. So perhaps our acceleration is equal to our change in velocity by our change in our time. And that's all it is our acceleration. If we think about our differentiation where we take a line and we're trying to explain this curve, is exactly the same because we have a change in velocity and the change in time. Typically this time is constant, is a constant interval. So we can actually begin to do a bit of dimensional analysis with this and maybe explain what units we should be using for this. So if we think that our acceleration is equal to velocity, which is meters per second, multiplied by our change in time, which is also seconds, we can find that acceleration equals meters per second squared. Okay, so that's all right, but how do we actually work out some equations to help us deal with some problems? So we know speed equals distance over time. Distance over time, we've shown that at school, and you've used it in GCSE physics more than likely. But okay, let's start by drawing a plot. Well, now we're going to look at some acceleration. So what happens if I was to say, well, we're going to have some body which is changing velocity over time, its initial velocity is u, and its final velocity is v. Okay, so we can see there's a change in velocity at some point. This is our time zero. So we have time on this axis, and we have our change in velocity, so we call this velocity here, and we have our first value, which is u, our second value, which is v. So what we can say here is, well, we want to try and get back our meters per second to try and understand what's happened here, to find this distance. So we can potentially use an area, which we can calculate from this. Well, we know that we have our first value, which is u, which is going to be our initial value. So we're going to say our velocity v is equal to u. But how do we work out this difference? Well, we've shown that if we want to get to this velocity, we're accelerating at some point. So we know that we're going through time. This is a change, it's a gradient, or what we showed that A equals dv by dt, so the velocity, sorry, by dt. So clearly, all that is our gradient here is A, and that means we have a time component here, so that must be A plus A multiplied by T. And we can check these units just use our dimensional analysis. So this is a velocity, which is meters per second, equals another velocity meters per second, plus acceleration, which is meters per second squared, multiplied by seconds again for time, and that cancels out, so we know we have the correct units. Okay, so that's all right, but we've got this velocity, but how could we work out some sort of distance? Well, we have to think what we've just done. If we've gone from that we had speed equals distance over time, and then we went to our acceleration from here, and we said acceleration equals speed over time. Well, actually, perhaps if we know what the distance over time is equal to speed, we could say that, well, we know that speed, or we'll call this u, or v, equals distance, distance over time. So how could we get back to this? Well, actually, if we integrate v with respect to t, doesn't this mean that we would get our original d? So yes, it does. So it actually means we can get our original d. So I'm just going to change our letters here. So when we're using these equations, typically s is the distance. So this will just stick with the handbook. So what we can say here is our distance s is equal to our integral. So our velocity here, which is u plus at, and that's with respect to dt. So if we knew that our first velocity, our original velocity was 0, and our top velocity was t, then actually we've got an equation and we know how to integrate this. So what we can say now is s is equal to, we'll just integrate it, which would be, we bring the power down, multiply, we're doing it with respect to t, so that'll be ut plus a t squared all over t. It's a definite integral t and 0. So what we actually find now is that s equals ut plus a half at squared. We have a second equation. So likewise, what we can easily do is we can also show that we can show from this equation that v equals u plus at, v equals u plus at. So if we do some manipulations, what we can find is we now have a second equation where we can say that s equals vt minus a half at squared. And all we've done is we've substituted this into here. Okay, so that's another equation. So what we have here is it say from that we can actually say, well, we can do some more manipulation. Is what happens if we were to try and get rid of, so we start with s equals ut plus a half at squared. We can actually say, well, s equals ut plus, well, we can bring our equation from earlier, and we can say that t equals v minus u over a, what we found out from here earlier on, from this equation. So we can then stick this into this equation here. So we can say that this would be, we'll start this, s equals ut plus a half. Our a, we're going to put it in terms of a, which is equal to a equals v minus u over t. So we can say that that would be v minus u all over t multiplied by t squared. And we can say that would be ut plus a half vt minus a half ut. And then we get a third equation which says s equals a half v plus u t. So we have another equation. So we're quite able to keep on manipulating and manipulating. So what happens if we were to say finally, by removing t, if we can get rid of this, we could say here that t equals v minus u over a. So we could perhaps sub this in. So if we take this equation, we can say that s equals a half v plus u multiplied by v minus u all over a. And then we get some brackets here. We'd say that that is equal to a half, expand that out, v squared minus uv all over a plus uv plus u squared all over a. And that would then equal to v squared minus u squared all over 2a. So we can finally say that v squared minus u squared equals 2 times a times s. And that's our next equation. So what we've done here is we've created 5 equations, which are s equals a half ut plus a half at squared. S equals a half vt minus a half at. So I've written those wrong. Start again, sorry. We found these 5 equations. I'll just delete those, copied them wrong. We have S equals ut plus a half at squared. S equals vt minus a half at squared. We have S equals a half v plus ut, and we have v squared equals u squared plus 2as. Have we got them all here? We have that one. We have 1, 2, 3, 4, and we have our 5, which is v equals u plus at. So v equals u plus at. So these are all of our equations of motion. So you could derive these, but don't worry, these will be in the formula sheet on the exam paper. You can remember them. Often they fall, once you've done them 10, 20, 100 times, you will remember them. So let's actually find out what they're for. Let's do an example. So let's start with question A here. And the question states, a particle starts with a velocity of 3 meters per second and moves with a constant acceleration of half a meter per second along a straight line AB. It reaches a velocity with 5 meters per second. Find first the displacement from A to B and how long it takes to travel. So what we can do here is we can begin to fill out our terms. So we know the initial velocity, which again, if we look back to our original plot, we called u. So our original velocity, u, equals 3 meters per second. We know that a equals half a meter per second squared. And we know that the final velocity, v, equals 5 meters per second squared. And we need to find, first of all, we need to find the displacement, s, and we need to find the time, t. Okay, so we can just go to our equation. So if we wanted to find s, that would mean that we have v squared equals u squared plus 2as. That would give us this. So from this, we could say that v squared equals u squared plus 2 times a times s. So that would be 5 squared equals u squared, which is 3 squared plus 2 times a half times by s. And if we rearrange that, we would find that our answer would be s. S squared equals, S equals 5 squared minus 3 squared, all divided by 2 times 0.5, and our answer S is equal to 16 meters. So all we're doing is sticking this into the equations. It's just simultaneous equations. And now we have a question. We could probably use a few of these equations, but we want to find T. So our simplest way is to say V equals U plus AT. So V is our first, so V equals U plus AT. So V equals 5 equals 3, which is U multiplied by U plus a half times by T. So we can find out that T would equal 5 minus 3 multiplied by 2. So our time would equals 4 seconds. So what we've done is we've managed to create this set of equations, which is describing acceleration. From just doing some simple differentiation and integration, we can actually solve something pretty cool. So maybe if we do now another example, maybe a little bit more difficult. So the second question B. So a particle starts from rest, so our u equals 0, at point 0, and moves on a straight line with an acceleration of 2 meters per second. At the same time, another particle behind it, so this is maybe P1, P2, a particle behind it, 12 meters behind the particle, so our S equals minus 12, also begins traveling the same direction of a velocity of 5 meters per second and an acceleration of 3 meters per second. So what we have here is we have two particles next to each other, one here, one here. There's 12 meters difference between the two, 12 meters. This one is going at where its velocity is 5 meters per second, its acceleration is 3 meters per second. Okay, this one here is our second particle, has an acceleration of 2 meters per second, and it actually starts from rest, so its original velocity is 0. So how are we going to solve this problem? So what we need to say is, so for A, we know where u equals 0, we can find out a distance and a time. So we know our acceleration is 2. So what we could say is s equals ut plus a half at squared for our particle 1. So where 2 is that, so s equals ut plus a half at squared. So we can say that this equals 0 times t, which we don't have anything for, plus a half times by a, which is 2, so that will just be, the answer is just t squared, which is here, so s equals t squared. So we've simplified this quite nicely. So we know the distance where they're separated equals 12 meters. So we can say that 12 equals t squared. So 12 equals t squared. So we've got the distance here, and now we want to work out for our second particle. So our second particle is s, our distance, which was s, and we have minus 12 meters. So we're going to add 12 onto here. S plus 12 equals ut plus a half at squared. Okay, so this is our separation between the two. This is what we're going to catch up. So we can say s plus 12 equals our original initial velocity, which was 5 meters per second, multiplied by t, plus a half times by the acceleration, which is 3 meters per second squared. Oops, I'm not going to put second. 3 multiplied by t squared. So we can say that our s equals 5t plus a half times by 3t squared minus 12. Oh, we have some sort of simultaneous equation. And what we also have is we have two parts for s. We've just said that s is equal to t squared. So what we can say here is our s is equal to c squared. This goes in here. So t squared equals 5t plus a half times 3t squared minus 12. And if we begin to tidy this up a little bit, we would find that we get t squared, oh no, we can say a half t squared plus 5t minus 12 equals 0. And that would be the same as saying t squared plus 10t minus 24 equals 0. And then if we then use our simultaneous equations, so we could probably just stick this into our calculator and say t equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a, which is the same as saying equals minus 5 plus or minus the square root of b squared, which is 5 squared minus 4 times by 0.5 times by minus 12 all over 2 times by a half, and we can say that would equal to minus 5 plus or minus 7 over 1. So the answer either would have to be negative 12 or 2. So we can't actually have a negative answer because the balls are going forward, so the answer would have to be 2. So the time it takes for one ball to overtake the next ball is 2 seconds. So it asks us the distance, how far it's travelled. Well, that's quite easy because now we know the time, we know our original data, so we can say s equals ut plus a half at squared. We know from our particle 1 that our velocity was 0 and our acceleration was at 2, so we can say the distance traveled equals 0 times t plus a half times by 2 times by 2 squared, and that would be equal to 2 squared times by 2 would be equal to, this would cancel with this, s would equal 4 meters. Okay, so that's a bit more of a tricky question, but it's something that might come up. We'll just do one final example. These are just all about practice. So this is about firing something up, and this is to do with gravity. So it says a rock sample is fired vertically upwards with a speed of 45 meters per second. So U equals 47 meters per second, okay? How long will it take the sample? How long will it take the sample to return to the ground? Okay, so this is probably something quite useful. Where the acceleration of gravity is 9.81 meters per second. So we know gravity equals minus 9.81 meters per second. So effectively, we've fired this rock particle up and gravity is pulling it back down, just like the apple did on Isaac Newton's head. So this is quite simple because all we need to say is we know that the initial velocity has to be 47 meters per second, and we know that the final velocity would then therefore have to equal the point at which it comes back down again. So if we take our original velocity where u equals 47, so our final velocity must equal minus 47. So it's gone all the way up and it's come all the way down. So that would mean that our acceleration would be 0. So v equals minus 47 meters per second. Okay, so all we need to do here is just stick this into our equation where we can say that v, we have u, we have v, we have a, and we want to find out t. So we can say that v equals u plus at, therefore t equals v minus u all over a, and therefore we can say that t equals minus 47 minus 47 all over minus 9.81, and the answer is 9.58 meters per second. 9.58 seconds. So this is just a few examples of some Suvat equations. We're going to touch on this a little bit in next lecture, but that's it just for this lecture.